Hello. So, hi everyone. Welcome to today's session on linear algebra to geometry. This is an NPTEL session, tutorial session. So let's wait for a few more minutes so that everyone can join, and then we will start the session. Hi everyone. Once please confirm that I'm audible and is my screen visible? Hello, am I audible? So I think there is one student. Satinder, can you confirm if I'm audible? Great. So my screen is also visible. So let's start today's session. Fine. So before starting today's session, I would like to give some few introduction on the notes on the topics that were covered in today's session. Right. So again, yeah, in the last week also, I think there was a mistake in solving one of the problems. So there was a numerical mistake that I did for the question number one. So let me rectify this here itself. Right. One of the students I just pointed out this. So Given the give the reflection matrix that reflects any vectors about the plane y equals to x in the Euclidean xyz coordinate system, right? So the formulation that we wrote for a reflection matrix is so reflected vector. So the reflected vector can be computed as original vector v minus uh, what do we say v minus okay, sorry, yeah. Original vector v. Let me write this like this. So let's say we have a vector v and we have a plane pi, right? So we want to find the reflection of vector v along the plane y pi that passes through origin, right? So such that as pi 0 comma 0 equals to 0, right? So now you want a reflection. So we can always say, and let's say pi perpendicular, the normal to the pi is n, right? And let's take it n cap, which is the normal unit vector. Then we can write v as c1 into v's component along pi, right? V's projection on pi plus c2 into v's projection along the normal. So we can write V as two components, and then you will see that if you look at the geometry, you will see that V reflected would be C1 V's component on pi minus C2 V's component on n cap, right? So this will be the reflected vector if you look through it geometrically that we discussed in the previous session only. And now what we have to do, we just have to figure out what will be V pi. So what is the projection of V along pi and what is the projection of V along the perpendicular vector to the plane pi, right? So let's say this is your plane pi. So, so let me just move here. And yeah, so this is my plane pi represented at y equals to x. Oh, sorry, defined as, sorry. Pi defined as y equals to x, right? So now our plane is given, so we can always figure out the normal vector. Normal vector is uh, minus one by root 2. Unit normal vector minus 1 comma 1. So that we have already written here, right? We have written this. So this is our normal vector. We have already identified the normal vector. And then what is the how to compute the V's projection on n cap? It is simply V dot n cap, right? So it will be V2 minus V1 by root 2. So this is here step 2. So this was step 1. Step 1. Then this was step 2, right? And then we want to find V pi, right? So yeah, Q is basically V pi, right? Q is basically V's projection on the plane pi, right? So we know that we know this relation that so let me call this equation 1 and this equation 2. So we know this from 1 we can say that V equals to V's projection on n cap, right? Plus V's projection on pi, right? So this is basically V's projection on pi. Fine. Now from here we can find V pi. So this is equals to V pi. So V's projection on the plane pi. And then from here we can find V reflected, which is V pi. So this is again V pi. Sorry. This is plane pi, right? Minus this now this entire component is v n cap, right? Now just put in the values here, right? So okay, so let's call this equation 3. This is equation 3. So from 3, right? From here 3, I can replace the value of q. So it becomes v minus uh okay. Right. It becomes v minus 2 into, so basically q is itself is v minus v n cap, right? This part. Uh, okay. Yeah. So this part in q, right? In the equation of q, this part is basically v n cap, right? And you are saying q minus v n cap. So it becomes v minus 2 into v n cap, right? So v minus 2 into v n cap. This is, oh, sorry. This is from 3, right? And then, so you can always say q minus v n cap. Q is v pi. V pi is basically v minus v n cap. So it becomes v minus 2 v n cap, right? This is v reflected. Now what you have to do, you just have to put in the values. So v reflected equals to v. So v reflected is equals to v minus 2 into v n cap, which is v2 minus v1 by root 2, right? Into n cap. What is n cap? 1 by root 2 into minus 1, 1, 0, right? So n cap is this value. Just put in the values. Now just do some arithmetic to figure out that this root 2, these scalars will get multiplied, and root 2 into root 2 will give you 2, right? So this denominator becomes 2. In the numerator, we already had 2, so these two cancel out. So final equation you get is v1, v2, v3 minus v2 minus v1 into this minus 1, 1, 0, right? So these two get cancel out, and then you write this equation as v1. So the total sum is v1 plus uh, v2 minus v1. So minus minus plus. So v1 of the first component, the x component, is v1 plus v2 minus v1. Second term is v2 minus v2 minus v1, or third term is v3 minus 0, right? V3 minus 0. So that is v3. Now you just find the solution, right? v1 minus v1 cancels out and you get v2 here. Then v2 minus v2 cancel out and you get v1 here, right? And then v3, v3 are here. So the reflected matrix, so input matrix or input was this vector, right? This was our input vector and this is our reflection, right? This was our reflection. So now which matrix essentially maps these vectors, right? So I can say V reflected equals to MV, where M is a, this is a reflection matrix, right? Reflection matrix. So what should be the entries of this reflection matrix? So you can clearly see that this is a kind of interchanging the rows, basically row of this vector, right? So row 0 is interchanged with row 1, and row 0 is interchanged with row 1, and row 1 is interchanged with row 3, and row 3 remains the same. So you get this matrix. This is a permutation matrix, if you know this. So this is a permutation matrix that gives you this transformation. So this is the correct answer. So the last time I did some mistake where I was missing this square root 2 factor in the denominator while writing the n cap. That's why the answer was different, but now I have corrected it. Fine, everyone. Is this clear? It's just a clarification for the previous session. I think Satinder, you raised a query that the answer was wrong. Am I audible? Okay. So basically the concept was right. There was nothing wrong in the explanation that I gave. It's just that there was some numerical mistake in the solution. Right. Okay, fine. So this was it. So let me start with today's notes, right? So in this week 7, what you have seen in the NPTEL lectures is number 1, solution of the linear equations in 3D, right? So we already saw these linear equations, how to solve the system of linear equations. And now in 3D, the only thing that changes is you get three column vectors and you try to find the linear combination of those column vectors to get the final output vector, or you have three rows and you do perform some Gaussian elimination over the augmented matrix to get the solution, right? So that's the thing, we are saying it as tetrahedron. So let's look at this tetrahedron, right? So basically, what does AX equals to B mean? So let's say your matrix A, you have a matrix A, which is a 3 by 3 matrix. So it contains three vectors of three dimensions, A1, A2, and A3, right? So now when you look at these three vectors, so let's say this is vector A1, this is vector A2, and this is your vector A3, right? So when you take unit vectors along these three vectors and try to join them all to form some sort of polygon, some sort of volumetric object, you will find that it forms a tetrahedron, right? So it's a tetrahedron. So let's make it more intuitive for us. So let's say this was A1, this was A2, and this was A3, right? So when you join these unit vectors, you get this kind of structure, which is always also known as a tetrahedron. So the thing is, when all these three column vectors of the matrix A are independent, then you get this kind of tetrahedron, which is a three-dimensional structure which can span the entire 3D space. But let's say if any of the column vectors are linearly dependent on each other, then you will see the cases where you will get a plane instead of a line. And if you are instead of a 3D volume, so if you are only able to span a plane, there are possibility that you will get no solution, right? So again, in this case, the determinant of the matrix A. So yeah, let me correct this. This is determinant of A not equals to zero, right? So if they are linearly independent, you will get a tetrahedron formed by the unit vectors of those three column vectors. And you will find that the determinant of matrix A is not zero. And from here, you can always say that there is one unique combination, linear combination of these three vectors that gives you the solution. Fine. Why this is unique again? So let's take a very basic example, right? So let's say we have this three-dimensional space, X, Y, and Z, right? Now let's say I form a matrix like this, 1 0 0 0 1 0 0 1, right? Now can you tell me the number of ways you can write any vector in the 3D space? Let's say I'm taking a vector B as 1 2 3. So in how many ways can you write this vector 1 2 3 as a linear combination of these three vectors, 1 0 0, then 0 1 0, and then 0 0 1? Anyone please answer this? In how many ways you can find this vector, which is a sum of these three vectors? Only one way, right? Only one possible way. So that's why we say that that's a unique solution, because there is only one way to get to the solution. There are no many multiple coefficients that can lead to the same solution, right? So so that is essentially, so what I question I asked is essentially another way of asking to you to solve the linear systems of equation Ax equals to B. Fine. So now, yeah, this is right. So if the determinant is non-zero, now if the determinant is zero, what happens? So if the determinant is zero, then we all know that one of the, yeah, either one of the vector is zero entirely, or it is linearly dependent on the other, right? That's right. And now let's say I'm considering in the 3D space, I'm considering this matrix M 1 0 0 0 1 0 0 0 0, right? Now, which space is this matrix spanning? The column vectors of this matrix spanning? They are spanning the 2D space, XY plane, right? So the values along the Z axis are up completely lost. You can only span this XY plane, right? So any vector present in this XY plane can be spanned using these column vectors. So any vectors can be represented at there. um, as their linear combination. Everyone, do you agree with this? And everyone, do you agree with whatever I am explaining till now? If you have any doubt in this, whatever I have explained till now, please ask me right now. Everyone, please type in the chat box. If you don't get it, please tell me. I will explain again. Good. So yeah, let's go back to my question. So we saw the first case, right? Geometrically, we saw the first case, case A, right? Where we form a tetrahedron, we get a tetrahedron formed by the three unit vectors of the column vectors formed by the column vectors of the matrix A, where we are trying to solve the equation A equals to B, Ax equals to B, right? But yeah, so there is first case where you get a tetrahedron which says determinant of A is non-zero, and you can only find one linear combination of all the three column vectors that leads to any unique vector B in the 3D space. Fine. So this is what we have established till now. So let's start from here. Now the second case, option B, second says we can have infinite many solutions. So let's see geometrically when it happens. It happens. Let's say we consider this basic case. So let me just get more space here. I don't have a space here. Hmm. Okay, let me do this here. Yeah. So now we are considering the second case and we are trying to solve this system of linear equations. Ax is equals to B, right? Now A is a 3 by 3 matrix that contains the column vectors A1, A2, and A3. All these three vectors are three-dimensional vectors, right? And B is also a three-dimensional vector, 3 cross 1, right? Now, the first case we saw that they are linearly independent and you get the solution, right? Now let's take this case. Now let's say our matrix A looks like this. A looks like this: 1 0 0 0 1 0 and then 0 0 0. Now let's take out the column vectors of this matrix A and plot it on the Cartesian plane that we know, right? So this is our Cartesian plane, right? There are three bases. This is x-axis, this is y-axis, and this is our z-axis, right? Now, the thing is, what is the vector? First column vector. So let's take on the first column vector 1 0 0. So this is this vector, right? This starts from origin and goes 1 unit towards the x direction. Then the second column vector is 0 1 0, right? Again, 0 1 0 is this vector that starts from here and goes 1 unit in the y-axis, right? And the third column vector is 0 comma 0. So basically it's the zero vector at the origin, right? Now, what is the space that you can form a span using these two vectors? What vectors can you form from the linear combination of these two vectors? You can only span the xy plane, right? So z plane is not even accessible, right? So basically, let's say if I have a vector, let's say 0 0 1. Can we get to this vector using these columns of this matrix? Can we? We can't, right? Right? We can't get this vector, right? Why? We can see the structure of the matrix. It's a singular matrix, and its column vectors are essentially spanning only the xy plane. So any quantity in the x z axis will not be spanned by covered by these bases, right? So now what I'm saying is, in this case, in these kind of situations, let's make some inferences from here geometrically. First one is determinant of matrix A is 0. That's true. We all know that. If any row or column of a matrix is entirely 0, then the determinant has to be 0. This is the first thing. That is, matrix is singular. You can say it's singular, or it is rank deficient, and whatever other properties you want, right? These are all different kinds of properties. But this tells us one most important thing, that is, either if we try to solve the system of equation Ax equals to B, so either we can have infinite solutions or we can have no solution. right? These are the two cases that we can have. Fine. Fine. Now how to say that? How to get to that, right? In 3D. In 3D, right? We are doing everything in 3D, right? Now, this is a very simple case. Now let me show you an example where you will get infinite number of solution using this situation, right? Now let's say our B vector is 1, comma 1, comma 0, right? Then for this B vector, our linear combination would be 1 into column 1, 1, 0, 0, plus 1 into column 2, which is 0, 1, 0, plus 0 into column 3, 0, 0, 0, right? Fine. This is correct, everyone. So basically X will be this vector. This is the column view of the matrix vector product, right? You can always figure out this. Now let me take another vector B1 that looks like this, 1, 1, 1. For this case, you can say X equals to 1 into 1, 0, 0, plus 1 into 0, 1, 0, plus 0 into, okay, sorry, yeah, this is not the right case. Um, Let me think of a good example. I'm missing something here. So yeah, yeah, I got it. So basically what is happening is I am using two vector essentially uh hello.
We can change y coordinate, then still we will be able to represent, I think so. X or
No,
y, any
but that won't be a solution, right? You
okay,
can't
that
represent.
will
So let's say
uh,
y coordinate. How come?
like z part to 0, I think. One
Uh,
one zero. So if you take 1 2 0, so that I think
okay.
that can be also expressed one time of 1 0 0 plus two times of 0 1 0 plus 0 times we'll get still plus two
But this
times
is
of.
not the same solution, right? This is not the same linear combination, right?
Okay, okay.
So this vector is essentially 1, comma 1, comma 0, and this x is essentially 1, comma 2, comma 0, right? These are completely different vectors. Fine.
Yeah, got it.
So this is not the case,
Uh,
right? This you can't
okay,
do.
so what we want, like 1 1 0, we want to express in the infinite number ways.
Hmm?
For 1 1 0 vector, what we want, infinite number of solutions in this case.
Yeah. We want some example where we can get infinite number of solutions to that in this case, but when we get infinite.
Sir, this example is fine, I guess, no? The last coordinate, you can have it anything, any non-zero thing. So
Yeah, right.
that
But
0 0 0.
you can't represent that vector, right? Let's say you have 8 here, right? What will be the combinations? You will never get to this B, right? 1, 0, 0 plus, let me write this 1, 1,
No, no,
right?
no, 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 no. Sir, coefficient is 8. B would be still same, no? So you are looking for Ax equal to B's solution, and you are saying that Ax equal
Okay,
to B
right,
can
right.
have infinite
Yeah, so
solution.
you're right. Sorry, I missed it. Yeah. So yeah, what I'm saying is, yeah, I started doing other things. Let's forget everything. Uh, so basically, what I'm saying is, you can represent this B using multiple possible linear combinations of these three vectors. How? So right now, this linear combination of these three vectors was 1 first column plus 1 into second column plus 0 into third column. I can always say that this is always equals to x equals to 1 into 1 0 0 plus 1 into 0 1 0 plus 1 into 0 0 0, right? This again gives us the same B. Do you agree, everyone? So this is again the same B. B, right? 1, 1, 0. In fact, you can always write this as B is equals to 1, 0, 1, 1, 0, 1, 1, 0 for X is equals to such that right. So this is not X equals to, this is B equals to, this is B equals to. So such that X is equals to 1, 1, K, where K can be any real number, right? Even imaginary, I mean, K can be anything. K can be anything here. K can be anything here, right? So basically, now you have infinite many values of K, and you are still able to reconstruct vector B from the column vectors of this matrix A, right? So this is the case where you are getting infinite many solutions. Fine, everyone?
Got it, sir. That one you was trying to say.
Yeah. So let's move on to the zero solution case, right? So this was a very simplistic, simple example. You can always take planes that do not coincide with the xy plane. You can always take plane y equals to x and figure out these properties from there. And the last example I would like to take here is this was first case. Let me write this here for case 1.1 infinite solutions. Now, let's say the case 1.2, which says zero solutions, right? If the determinant is zero, you can have these two cases. Any one of these two cases can arise depending upon the matrix column vectors and the B, right? Now, let's say I take my B as 0, 0, 1, right? Now, do we have any X? Do we have any vector X is equals to x1, x2, x3 such that x1 into 1 0 0 plus x2 into 0 1 0 plus x3 into 0 0 0 is equals to b. The question is this: can we get to any vector? And you all can see that we can't get from here, right? So basically so no, right? We can't get, and we have zero solutions for this. So now in this case, what is happening? The vector b is 0 0 1. Now let's observe the vector b and the column vectors that we have. So vector b is again, let me take the plane, right? Right. So this is the x-axis, this is the y-axis. Now this is your column vector a1, right? This is your column vector of the column of that matrix A2, and A3 is obviously 0. So let's ignore this. And let's talk about the vector B. Vector B is protruding out in the Z axis direction, right? So it is perpendicular. So basically, it's too big. It's a unit vector, right? So it has to be proportional. So now this is your vector B. Now what you can identify from here is there is no combination of A and B, A1 and A2, even A3, that will give B. You will never get that. So there is no possible solution. Why? Again, A3 is already 0. A3 is already 0. Now you got only A1 and A2. And A1, A2 are spanning only the XY axis. Now, if you have any vector that has some component along the Z axis, you can never get to that component using a linear combination of these two vectors. Another way to check out, think of this is basically when you do this, B dot A1, you will see that this quantity will be 0. B dot A2, this will again be 0. That means B is orthogonal, right? This is the orthogonality property, we know this. So orthogonal to the vectors A1 and A2, right? So basically B is a normal to the planes found by the vectors A1 and A2, and you will get zero solution. So these are the three cases that we saw geometrically. How can we get infinite possible values of values to get these solutions, right? So this is what we covered in 3D. Yeah. Anyone, do you have any doubts?
Yeah. Suppose if B vector is not 0 0 1,
Okay.
if it is some other vector, so what?
Mhm.
How will come to know that no? solution will be possible.
Again, you
So
only have to
by comparing only.
yeah, yeah, yeah.
Okay.
Now let's say your uh b vector is something like 1 1 1, right? You can't get to this vector. So it this vector is essentially protruding out in some z direction, which is not spanned by the vectors a1 and a2.
Like what I'm just thinking ki is here to A vector is what the transformation matrix A is there. Uh, uh, by looking only we can come to know okay no solution will be possible.
Yeah, yeah,
But
yeah, right.
if it is like some complicated A is there, then I think maybe some other process will be there.
Right. So basically, how to figure that out? You have to look into the column span of this matrix A, right? So what is column span? It's the space spanned by the vectors of its column, right? So matrix has A has t columns, A1, A2, A3. So what you have to do is you have to figure out look at the column span of these three vectors. Now, any vector that does not lie in this column span cannot be formulated by a linear combination of these three vectors. So by
Uh,
just by looking at the matrix A, you can
okay.
find all the set of
Uh,
vectors that will
okay.
give you a zero no
Uh,
solution.
uh, 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 I think the Gauss Jordan method only will be useful in that case because number of free radicals or number of pivots we can see that whether it is there or not. Like Gauss Jordan method is there, na?
Yeah, yeah,
Gauss.
hmm, yeah,
So by that rank is less, so infinite or maybe that, and then we'll see the third coordinate and we can come to know. I think
yeah.
that only approach.
Basically, yeah, you will see that in the last row will essentially become zero entirely. So
Yeah.
when you try to now you want to take some difference, divide by this quantity and do something that's not possible. You can't get it to the form that you want.
So I think that that
Just
only will
yeah.
uh, got it, sir.
Hmm. So everything like solving this problem has multiple ways, but everything boils down to this concept of the span of the column vectors of matrix A. So because of this property, you will figure out seeing that in the Gaussian elimination it won't work. And why it's not working, again, you can't get to the vector that is not in the column span of this vector, column span of the vector of the matrix A, right? So everything boils down to this column span of vector A. From there, you can figure this out. Fine. Right. So yeah, this was it. So the second thing that you saw is solution to homogeneous system of equations. So basically that says AU equals to 0 such that U is not equals to 0. So basically there are two cases when you try to solve these kind of equations. One is for homogeneous system of equations. The one solution is U itself is 0. This is known as a trivial solution. So this is straightforward. You don't need to think of some anything. It just exists. It exists always, right? If U is 0, AU will be 0, right? For any kind of matrix. But we are more interested in non-trivial solution where U is essentially non-zero and still you are able to get AU equals to 0. So this brings us to your question, right? So how can we figure out whether which kind of vectors will give you no solution. I mean, will give you zero solution, right? Value zero, which are not in the span of this matrix A, right? So non-trivial solution may what we want u such that u dot a1 equals to 0, u dot a2 equals to 0, u dot a3 equals to 0. So why I am always going back to a1, a2, and a3, where a1, a2, a3 are column vectors of this matrix A, because we are interested in the columns the space spanned by the column vectors of the matrix, right? Now, if the space spanned by the column vector of the matrix is perpendicular to our vector, then you can always say AU equals to 0. You can always find a non-zero u such that AU equals to 0, right? Now, when these kind of solutions are possible, trivial and non-trivial. Now let's look into when this will appear, right? So case one, when A1, A2, A3 are linearly independent. So basically A1, A2, A3 cannot be written as a linear combination of the other two, right? That is the determinant of the matrix found by the vectors A1, A2, A3, that is A, will be non-zero, right? The volume of the tetrahedron formed by these three vectors will be non-zero, right? So in that case, only trivial solution is possible, because in 3D space you are actually spanning all the vectors possible using these three independently independent vectors, right? There is no vector that you cannot sample using these three vectors. You cannot model using linear combination of these three vectors. All the vectors present in a 3D space can be found by three linearly independent three-dimensional vectors in the 3D space. That's it, right? So this is the case one. So the only solution for u is possible when u is equals to 0. Case 2, when a1 and a2 are linearly independent, but a3 is a linear combination of a1 and a2. So what does this case look like? This case looks like a some sort of triangle, right? It looks like a plane. So basically these vectors are a1 and a2, and a3 lies in this span, right? Let's take my a3 vector here, right? Oh, sorry. So this is my A3 vector, which essentially lies in this span. This is my A3 vector, and A3 is essentially C1 A1 plus C2 A2, right? So A3 is a linear combination of these two. So in this case, you will find one thing, that determinant of the matrix A is 0. Why? Again, you want to find the volume of the tetrahedron formed by these three vectors, right? What is the volume of for volume of a tetrahedron formed by vectors which lie in the same plane? It will be 0, right? Yeah, fine. Now, yeah, this is it. Then, huh. So in this case, in this case, what will be the value of u? The value of u will be um, a vector which is perpendicular to the vectors a1 and a2, right? So this will be this vector, such that this forms a vector 90-degree, right? So let's how will it look like? This is a vector, right, which forms up 90-degree with this plane, right? This is the vector u. In this case, you will get infinite many solutions. Again, why infinite many? Let me explain you why. You can always say that so this is a vector u which is perpendicular to the vectors a1, a2, and a3. Essentially, it is perpendicular to a1 and a2, orthogonal to a1 and a2. And since a3 can be written as a linear combination of a1 and a2, it is also orthogonal to the vector a3, right? That can be proven. I hope you can figure this out by yourself right by now, right? Now the next thing is, how can we claim that there are infinite possible such vectors? Why? You can always say that u is a vector by using a simple property, that any vector in the direction of this vector a1 cross a2, any vector in the direction of this vector will belong to this solution space, right? Since a1 cross a2 is perpendicular to a1 comma a2 comma a3, right? So in this case, you can scale in that orthogonal direction, that is the normal to the plane found by the vectors a1 and a2 any times, right? Any value or scalar value can be chosen to scale the vector in that direction. And if you take a dot product of that vector using these from these two vectors, you will get value 0. So there will be infinite possible values of u that will give you AU equals to 0, right? So this is the case 2, where A1 and A2 are linearly independent, and the third one is linearly dependent on the right. Right. The third case is case 3. In case 3, what we are looking, A1 is a vector, and A2 and A3 are linearly dependent on A1. Basically, all the three vectors lie in the same line, right? All the three vectors lie in the same line. This is what this line is saying. This is saying a2 equals to c1 a1 and a3 equals to c2 a2. This is essentially saying that all the three column vectors of the matrix A are lying on the same line. Now in the three-dimensional space, let's think of this. in the 3D, so in the 3D space, you have this x, y, and z, x, y, and z axis, right? Right. Now, you have three vectors that all three belong, basically point in the direction of the x-axis, right? So let's say this is the direction in which all the three vectors lie, right? A1, comma A2, comma A3. Right. Now, how many vectors are there which are perpendicular to this these three pair combination of vectors? So essentially all the vectors in the YZ plane, right, everyone? All the vectors in the YZ plane. So let me draw this plane as a circle, right? So all the vectors in the YZ plane are perpendicular to these vectors. So now not only not only any possible scalar in that direction, right? You also get any possible scalar as well as any possible direction in the plane perpendicular to vectors a1, a2, a3, right? Will be a solution to the system of equations a u equals to 0 such that u is not equals to 0. Fine. So this was the third case. So I just geometrically showed what is essentially going on in the space. So basically, if there are at least two independent vectors, you will get a direction only, and in that direction, you can have infinite possible values of u by just scaling that vector, which is an again you are looking at a plane and you want to find a normal to this plane. There is one single direction, unique direction, but the normal along the normal you can have infinite possible vectors with by infinite possible scalings. If all the three vectors lie in the same line, then you get a space, entire two-dimensional space, perpendicular to the three columns, right? So let's say this is the direction in which all the three column vectors align. So now this is my hand is the plane, which is essentially perpendicular, right? It is perpendicular to this direction, and then yeah. So you can have infinite many possible directions as well as scaling to get the infinite possible solutions for you, right? So this is a solution to the homogeneous systems of equations in 3D. I hope everything is clear till right now, right?
Uh, e- Excuse me, sir.
Ah,
Like we have two cases now. One case is AX equal to B.
hmm,
So if in the A matrix, whatever
hmm,
the A1, A2 vectors are there,
hmm,
so if they are linearly dependent,
hmm.
so in that case, we are going to get no solution or infinite many solution.
Uh, but if they are linearly dependent, right?
Yeah.
Yeah.
So in that case, what we'll get? No solution.
Either no solution or infinite solution, right?
No infinite. I think we are not going to get because B AX equal to B, so we are not going to get B matrix. I think B column will not get B
No, no.
vector. We will not get if
What
it
is the question? What is your question, right? I am not getting
like
it, I think.
uh, we have two situations. One is for homogeneous.
Hmm. So
Second
let's
is
consider the non-homogeneous case, right? AX
yeah.
equals to V first, and then we'll
If
go to homogeneous.
for in A matrix A1, A2, and A3 vectors, they
Hmm.
are linearly dependent.
All the three are along the same line, right?
Yeah.
Okay.
So in that case, we are going to get the solution or not. That I want to know.
That depends on the vector B, right? So now let's say B, let's say I'm saying the vector B is essentially C1 times A1, right?
Yeah.
Now, what are the possible rescalings and addition of the vectors A1, A2, and A3 such that you get B, right? So K1 plus K2 plus K3. The thing is, there are infinite possible values. How? Let's look at an example. So let's say our vector A1 was 1, comma 0, comma 0. A2 was again 2, comma 0, comma 0. A3 was again 3, comma 0, comma 0. And our vector B was essentially 4, comma 0, comma 0, right? So let me. Yeah, someone whose mic is on, please. I think there is some noise coming out. Okay, fine. So this was A1. A1 was 100. This was A2, which was 2 comma 0 comma 0. And this was A3, which was 3 comma 0 comma 0. And we want to say that, so matrix A, and I want to say that A into X equals to, sorry, A into X equals to B, where B is essentially 4 comma 0 comma 0. So now let's try to solve this equation, which is equals to, uh, let's say 1 into 100 plus 1 into 200 plus 1 by 3 into 300. Do you agree that this is a solution? For this, you will get an x of 1 by 3. Do you agree with the solution? Or, so just tell me if you feel that my answer is wrong, right? I can say 100 plus 0, 200 plus 1300, right? Now again, in for this case, you get an x of 101. Do you agree with this? Both these, you are seeing that you have two values of x that get to a same value of p. So essentially, there are essentially infinite possible linear combinations that will give you p. So that's why there is a possibility that you can get infinite many solutions. Is this clear?
If yeah, if B direction is not in that same,
If it's not
if
in that direction, then obviously you are getting a zero
okay,
solution, no
or
solutions. And also be, let's say if only two of them are linearly dependent and one is linearly independent of the two, then again you can get B with no solution or infinite many solutions. If B lies in the plane of the two vectors which are linearly independent, then you get infinite many solutions. If B does not lie in that plane, B is orthogonal to that plane, you get zero solution. So in both the cases, you can get either zero or infinite many solution for the non-homogeneous case. Is this clear?
yes, sir.
Great. So,
Sir, one doubt.
yeah, yeah.
So, suppose there are two vectors. The
Hmm,
last example that you gave,
hmm,
if B is orthogonal to the plane generated by
hmm,
that two, then
hmm.
it will be then it will have zero solution. So B need not be orthogonal, right? If B is only outside that plane, then also it's fine.
Right. Yeah, that also work. Yeah, let me correct this. B
Uh-huh.
need not to be orthogonal. B just need to have some component along the along a vector which is orthogonal to the plane. That will be the correct complete statement for
Oh,
that. Yeah,
okay, I got you. Actually, you are representing R3, no? So that's why
yeah,
I think orthogonality came there,
yeah.
right? Yeah. Okay, sir. Yeah.
Fine. I think you have another question like, what do you mean by direction plus magnitude, right?
Yes, sir. Yes, sir. You have wrote it somewhere, like in the last
This is
portion
this
in the
this
note,
example, right?
right? No, not in this particularly. In the note that you have prepared already.
Yeah, this one, right? So infinite many solution in the plane directions plus magnitude, right? So it's loading up. Just wait.
Yeah.
Huh.
Yes, sir.
This
Yeah,
one,
yeah.
right?
Right. This one. This one. Yeah.
Huh. So basically,
So
what I
by
am trying to say
magnitude, what
from
did you mean?
from this, what magnitude is essentially the scaling factor along that vector direction, right? So let's say you have a plane YZ plane, and all the three column vectors lie along the x-axis, right? So
Yes, sir.
in this YZ plane, you can have infinite many directions of of that vector, right? And along each direction, you can have infinite amount of scaling, right?
Okay. Yes. Yeah.
And that scaling is essentially the magnitude of that vector along that direction. So that's what I'm saying, that there are infinite possible value of magnitudes also. So let's say you are taking a vector
Okay.
0
Okay.
comma 1 comma 1,
Mhm.
then you can always take a vector 10 comma a 0 comma 10 comma 10. So there are two different magnitudes, right?
Oh, okay. Okay. Right. Right. Yeah. Got it, sir.
So any vector can be represented as a direction plus a magnitude. So that's basic definition. Yeah. Any other questions till
Yes.
now? So uh,
Uh, next was doubt for the homogeneous same situation. Like
yeah.
if the vectors are two vectors are linearly dependent, then
uh,
always it will be infinite many solution.
Okay, so for the homogeneous case, right? You want to say that is there a possibility that you will get no solution, right?
Homogeneous though will not get any no solution case though will be not there. That's the
because you
confirm.
are already having at least the trivial solution.
Hmm, hmm, hmm.
And for non-trivial also, you will have at least a vector which will be not lying in the plane of that
Hmm.
the span of those vectors, right?
So
Basically, in yeah.
I'm saying ki we can draw the conclusion ki if linearly dependent vectors are there
Hmm.
in homogeneous, so always it
Hmm.
will be infinite many solution.
Yeah. Because if they are if the column, let's say we are talking about the three-dimensional space and we have a matrix of dimensions 3 comma 3, each of the column of the matrix is a three-dimensional vector which is spanning this R3 space, which is 3 comma 3 space, right? Then if any of the two vectors are linearly dependent, then you always get a plane, right? Now in the 3D space, if you get a plane, then you always have a normal, right? A normal always exists, right? Do you agree with this? So if you have a
Yes, sir.
3D space and you have a two-dimensional plane, then there is always a normal which lie in the 3D space, and that is true. Like there is no contradiction to this thing. This is universally true. Everyone will accept this, and mathematically you can prove this that there will exist a normal always for a plane in the three dimension. Then if that exists always, then you always have a solution. AU equals to 0, and U is essentially the normal to that plane. If the normal also always exists, the solution always exists. That's it. Now, let's say if they all are lining along a vector all along a same single direction, then you just don't have a one single direction that is along the normal. You have entire space that you can have in which you can sample vectors. Now you have entire space, so you have infinite possible directions as well as magnitudes. So again, you don't have zero solution. You have infinite possible value of solutions. So this is what I'm explaining for this. Is this clear, everyone?
Yes, sir. Yeah.
Great. So let's any other doubts? Please confirm so that we can proceed. Fine. I don't think any other doubts are there, and hopefully, let's take them later on. Right. So so the next thing is very interesting thing, value decomposition. Right. So now let's take some scenario. Let's say you have to write some code, set up some algorithm, that what the task of that algorithm is to solve the linear system of equations ax equals to b, right? So the task of your system is of your algorithm or your machine or your calculator, whatever you call it. The task is ax equals to y, ax equals to b. Sorry, let's take b here, and you want to solve these systems of equations, right? So till now, what we have done is what we have done Gaussian elimination and tried to figure out the solution. There are multiple ways you can figure out if the matrix is if the matrix is a square matrix, right? And you can find its inverse, then also you can solve this problem, right? So till now, whatever we have covered is we have covered everything for square matrices, right? So let's think of square matrices. That's square matrix, right? So you can solve this. I know we all agree this. But let's say I have to set up some algorithm that does this and in a efficient and faster way, right? Why? Because let's say the solve is required for a large number of vectors. So let's say we have a set of vectors b1, b2, up to let's say b1 lakh, one whatever, right? 10 raised to power something, right? 10 raised to power 10, let's say. So there are 10 raised to power 10 vectors, and you want to find the solution for each of these vectors. Ax equals to bi, right? Where I belongs to the set 1, 1, 2, dot, 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 10 raised to power 10, right? Now, if you, first thing, a human will not try to do this. Second thing, we have computers, so we will try to write some algorithm and code it up so that this can be automated. The third thing is you want that code to be as efficient as possible, right? And the thing is, in numerical analysis, people just figured out these ways, these algorithms to make this process faster. And basically, matrix factorization was invented for this essentially. So basically, what happens is you try to form some, um, you try to write this matrix as some a multiple of two different matrices or any other thing, so that or as a product of matrices or a sum of matrices, if in future you will see this like L plus D plus U, something like this. So can you factorize the matrix? Can you write the matrix in this kind of form and try to get to the solution, right? And this will be faster. How faster? I want to ensure that after I do this, I am able to solve the equation ax equals to b such that lux equals to b, right? Efficiently, as well as I am able to repeat it multiple number of times. So if what you do factorization once, right? You factorize once and then simply you reuse it for each iteration, right? So for example, you are running 10 raised for 10 iterations here. So for the first iteration, you do the factorization and use the result of factorization in every iteration. So this is how factorizations work. And the interesting factorization that you have seen is LU decomposition. What it says is essentially you can always split a matrix A as a lower triangular matrix, right? A lower triangular matrix and a upper triangular matrix. I hope you know the definition of these matrices. So basically, lower triangular matrices have all the entries above the diagonal to be zero, and triangular are matrices with entries below the diagonal to be zero, right? So these entries are entirely zero, and there is this U matrix, right? So these entries are entirely zero. So basically, we try to find these kind of factorization. And now, if you have this, you can always try to solve this ax equals to b. That means lux equals to b. let's say let's say ux equals to y, then you can say ly equals to b, and then l is a lower triangular, right? Lower triangular. Now what does this mean? You can simply do back substitution to get the solution. You don't need to figure out the elementary row substitution one, right? Now from here you can figure out the value of y, right? Now if you know y, you can do ux equals to y, right? Again, what you have to do, this is upper triangular, and what you have to do, you have to do again a back substitution. Simple, right? Yeah, this is a possible motivation, Ron. You're right. Yeah. So basically, if a matrix looks triangular, either it's lower or upper triangular, you can always figure out the solution just by doing back substitution. You don't need to think of the elementary row operations again and again, right? So if you are able to do this, like you for each solution, for each solve, you only need two back substitution steps. You don't need to figure out those elementary row operations. Do you remember, right? In Gaussian elimination, we were trying to do. So we were trying to do R2 equal to some scalar times R1 plus R2, something like this, to make sure that the matrix is lower triangular in Gaussian elimination, right? So you do need to figure out that for each iteration. For only one single iteration, you have to figure that out, and after that, you can simply perform back substitution to get to the answer, right? This is all about LU decomposition. How to get to the answer? What does LU decomposition looks like? You already know this. Why? Because you all have done Gaussian elimination, right? Gaussian elimination. Now, what does Gaussian elimination say? So let's say you have a matrix M, right? You have some entries A1, A2, A3, right? And x equals to b, right? What you try to do, you try to do elementary row operations, elementary row operations, right? To get upper triangular, sorry, yeah, to get upper triangular. So basically you were doing this on the augmented matrix, right? You were doing this on augmented matrix to get upper triangular augmented matrix, right? Upper triangular augmented form, augmented matrix. And then what you were doing, this was the step one, and the step two was back substitution to get the solution. This is clear, everyone, right? I don't need to explain anything here. I don't need to get into the details that the matrix will look like a, yeah, right? Like A1, A2, A3, let's say, and then 0, A4, A5, then 0, 0, A6 into x equals to something b1, b2, b3, something like this. From here, you know, a6 into x3 is essentially b3. So you are just simply doing back substitution, right? Which is very fast. You don't need to think of anything here, right? So now, when you look retrace all the steps, right? You will see that that upper triangular form is essentially found by doing some operations on the matrix A itself, right? So what you are doing essentially, some matrix multiplication with A, E1, E2, E3 to get the upper triangular form, right? And these are essentially lower triangular matrices. How? Why I'm saying this? Please prove this after the session. But it's really easy. You just have to look into these matrices. So what you have to do? These are all 3 by 3 matrices, right? These are all 3 by 3 matrices, 3 by 3 matrices. And what you have to do? So let's say, let me give you an example. Let's say you are saying row 3, replace row 3 with row 3 plus 2 times row 2. Let's say I'm saying this, right? And you have some matrix A, and for this I am trying to apply this row transformation. How can you write this in a matrix form? Simple. You can say this as, now let's say this is our matrix A, right? A1, A2, A3, A4, A5, A6, A7, A8, A9, right? So now how to say this? So row 1 is unchanged, 1 0 0. Row 2 is unchanged, 0 1 0. For row 3, what I'm saying, this into this, right? So you do 2 into R2 and then R3. So everyone, please pay attention to this. What I have written here is, whatever I have written here, please pay attention to this. When you do these matrix product, right? Matrix product with A, E1 into A, you will see that this is essentially performing this uh, row transformation. Can you see this, everyone? Can you see this from here? If you understand this, then it's done. You don't need to think of anything else. Right? No one has any doubts in this. Can we proceed? Great. So now you know how to transform this elementary row operations into a matrix product, right? So now from the next time onwards, you are doing any matrix row transformation, just write them as a matrix. Now this was matrix E1. Now again, I will have some matrix E2. I will have some matrix E3 and so on. Ultimately, our matrix A becomes a upper triangular matrix, right? E3, E2, E1 into A equals to U. Now the thing you have to prove for yourself is that all of these E matrices will be lower triangular given that the matrix A is a full rank matrix. That you can prove. I know you can see the pattern from here itself, right? So how to get to that? Just think. You are always saying R3 is equals to R3 plus 2R2. So you are already updating the lower row from the with a scalar addition from the topmost row. So that is essentially a product with a lower triangular matrix on the right hand side that you can figure that out. So that's it, right? Now, if these are lower triangular matrices, so the first property, all the EIs are lower triangular, right? Second property is product of lower triangular matrices is lower triangular, right? This is also you can prove and you can show that this is some matrix, let's say L dash into A equals to U. You will get this. And this is a lower triangular, right? Now, if A is full rank, you can say that A equals to L dash inverse U. And let's call it LU, where L is a lower triangular, right? And U is the upper triangular. And this is the formula that you see. Simple. This is how you do LU factorization. This is the formula that you have been taught in the classes and whatever, right? Why it is useful? Now you know this. You have to do 10 raised power 10 iterations for linear solve. You don't want to figure out this elementary row operations for each iteration. What you do, you figure out this LU decomposition. Then you can use this kind of trick, right? You can use this kind of trick. After getting the LU decomposition for the first time, you can do this kind of trick where you only have to do backstep substitution 2 times for each iteration, and your algorithm will be really fast, right? So this is the use case of LU decomposition and why it exists, right? Now, does it exist for all kind of matrices? Is it true? Whatever. These are the questions that you can figure that out from the lectures also, right? And the last thing was least square solution. Least squares we will look into with an example. Let's go back to the examples, right? I really want to get back to the examples. I hope all the concepts are clear right now, everyone. So I will basically, I have explained a lot in detail about this. So I will be making this session a bit shorter for this problem solving session. I will solve the questions very quickly. And if you face any difficulty, just tell me, right? So let's solve question number one. So let A be a 3 by 3 matrix, right? A is a 3 by 3 matrix. Basically, it has three column vectors. We are spanning the 3D space. Consider the system AX equals to B. So you have to look at this, which is the case, which is non-homogeneous, right? This is non-homogeneous system. Fine. Which of the following is not a valid reference? So everyone pay attention to this. It is saying not a valid reference, right? So let's see what are the not valid references. AX equals to B has no solution if the column vectors of A are all in the same plane and B is in a different plane. So this is a valid conclusion, right? We already saw if all the vectors are in the same plane and B is in a different plane, then you get no solution. Is everyone agree with this? The solution is a valid right? This is a valid inference. Am I correct, everyone? If you face that I am wrong, just tell me, right? That's the way I will be proceeding from here. AX equals to B. Yeah. AX equals to B has infinite many solutions if the column vectors of A are all on the uh, same plane, right? It's not necessarily true. B has to lie in that plane, right? B has to lie in that plane. Then only you can say that. So option B is not a valid. This is not valid, right? Not valid. So your task right now is try to solve the problem with me. And if you are not getting the answer, what I am saying right now, just disturb me right now itself, right? So this is not a valid inference, and I hope every one of you now understand. Then AX equals to 0 has unique solution if A is invertible. Is that true? Anyone? A is an invertible matrix, right? And AX equals to 0 is has a unique solution. Anyone can you tell me what will be that solution?
A trivial solution it will be.
Yeah, it will be a trivial solution, and that will only be the solution. Why? Because again, you are spanning all the 3D space, so you don't get any other vector which is orthogonal to all the three vectors, right? Now AX equals to B. So AX equals to B has unique solution if the column vectors of A all are independent. Again, this is also valid. This is the very simplistic case, right? Valid. So option B is the correct option because the question was asking us, which is not a valid solution. So option B. Everyone, do you agree with this? Do you have any doubts? Please tell me. Let me use circles here. Circles will be good. So option B is correct answer. So we looked into it a bit detailed in this concept. So I hope by now everyone is able to understand what linear system looks like, how to solve linear systems. All the cases are covered. Fine. So let's move on to the next question. Fine. Consider the homogeneous system of equations. AX equals to 0, right? We are dealing with the homogeneous systems of equations. Let A be a 3 by 3 matrix, X and right. Let A be a 3 by 3 matrix and X and 0 are three component vectors. So basically X belongs to R3 and or C3, whatever you prefer, right? And 0 is basically origin 0, 0, 0, right? So which of the following is not a valid inference? Again, not a valid inference, right? As far as the homogeneous systems of equations is concerned. Again, I hope everyone gets the answer by now. The solution to X equals to 0 is that vector orthogonal to all the row vectors of A, right? Is this true, everyone? This is essentially true because you will see that for a square matrix, basically the row span and column span will be same. So I'm telling you that this will be true. I want you to prove this. Just think of this. You will get to the answer. It's not a big of this. You're just trying to look at the row span now. Now you had three independent row column vectors. So do we have three independent row vectors also? Right? Easy to answer. is just thinking of the transpose operation, right? So let's say A is a 3 cross 3 matrix and it has some rows which are linearly independent. So what about A transpose? It's a 3 by 3 matrix whose columns are linearly independent, right? Now you want to find the solution A equals to 0. Let's transpose entire equation. You get X transpose A transpose equals to 0. Just think of this, right? You will get to the answer. So option A is a valid option, right? Uh, Not a valid inference. It's a valid inference. The solution to X equals to 0 is the cross product of the row vectors of A. Okay. Cross product of the row vectors of A. No, it will be cross product of column vectors of A, right? Why I'm saying this? Let's see. This is not true. So let's say you have vectors 1, 0, 0, 0, 1, 0, and 0, 0, 0. Oh, it's a very simple case. Sorry. One, what can be the example? 1, 2, 0, 1, 0, and 0, 0, 0. Right? Now you want to find a linear combination of these three column vectors. You want to find the linear combination of these three column vectors, right? Such that C1, uh, such that C1 into 1, 2, 0 plus C2 into 0, 1, 0 plus C3 into 0, 0 has to be 0, right? And you can easily find a solution by taking the cross product of these two vectors. You will get the solution. But now the question is saying you just have to find the cross product of these vectors. Sorry, 2, 1, 0 and then 0, 0, 0. Right. So now the question is saying if you get a vector which is perpendicular, which gives you 0 with this matrix, then you get the solution, right? So let's figure out if it's true. 0, 0, 1. Hmm.
Sir,
Yeah,
may I add one point? Yeah.
yeah, yeah.
So, sir, so I'm thinking not in terms of a particular values. So
Hmm.
I'm thinking how so cross product is basically orthogonal, right? So A
Yeah.
cross B, it is orthogonal to A and B.
Hmm.
So what they're saying that AX equal to 0. So let's consider that A has rows R1, R2, and R3.
Okay.
Okay. So suppose you take cross product of any two rows. Basically, while
Ah,
taking cross product, we'll take any two rows, right? R1 and
yeah.
R2.
Hmm.
So and if you take cross product of R1 and R2, it will be orthogonal to R1 and R2.
Yeah.
So while we take AX kind of thing, while we multiply A with
Hmm.
X kind of a thing, so isn't it
Hmm.
the dot product of R1 with R1 cross R2, this kind of situation?
Yeah. Right. 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 Right.
But yeah, there's a glitch. Like I haven't thought about what if R3 is linearly independent. So I was
Yeah.
thinking, what if
Basically,
two are
R1.
linearly independent?
Yeah, R1 dot R1 cross R2 and R2 dot R1 cross R2 will give you the solution, zero values, but it's
Mhm.
not guaranteed that R3 dot R1 cross R2 will give you zero, right? This is not you can't say about this thing, right? So
Right,
you
right.
will get
Yes.
one non-zero component,
Okay, okay, right, right. Yeah.
right? I mean,
Yes,
this
sir.
can be seen through an example, but yeah, this was a really nice example. Thanks. So I was trying to bring up some contradiction to this by taking some example from the cases that we are familiar with, but this is a good example, I guess. So yeah, let me bring this up here. Right. So this shows us why option two is not necessarily correct. Why? Because Not a valid inference because let's say you have three R1, R2, R3 vectors, and I am taking the solution as R1 cross R2, then you are not sure that R3 dot R1 cross R2. It's not guaranteed that this will be zero, right? When so again, this again brings us to an interesting question. When it will be zero and when it will not be zero, right? So do you remember a formula that we saw that looks like this? This is a
So,
scalar triple product,
excuse me,
right?
sir.
Yeah.
If any two vectors are linearly dependent, in
Yeah.
that case, definitely it will be cross product one. If it is linearly independent, then it is not possible. I think so. Then trivial solution only will be there.
Okay, so you are saying if they are linearly
Any any
dependent, then
any two are linearly dependent, so
uh,
definitely the solution will be given by the cross product.
yeah, right, that's true. That's true. That we already saw. Yeah.
Hmm.
So basically, you can't say it directly, but yeah, brings to your thing, right? Satyendra, you are right. Basically, this can or cannot be zero. This quantity can or cannot be zero. It depends upon the vectors R1 or R2 and R3. Since we have no much information, option B is not true, right? And this is also a scalar triple product found by these three row vectors. So it is essentially the volume occupied by the three row vectors, right? So for that to be zero, the determinant of the matrix has to be zero. It must not be full rank, right? So let's get to option C. The solution is zero if and only if matrix A. So basically option C says x equals to zero is the only solution if and only if the matrix A is invertible, right? So this means trivial solution only exists if the matrix is full rank, that we already saw, right? So option C is a valid inference. So this is not the option answer
Sir,
that we want. Ah,
sir, in
yeah.
option C,
Hmm.
in option C, so
Hmm.
the thing that they're saying if and only if you have to
Hmm.
prove it, that
Hmm.
suppose A is invertible, then to I'm
Hmm.
guaranteed sure ki X is zero.
Yeah.
But suppose you are telling me only this fact, this rho
Hmm.
Ax equal to zero with X equal
Hmm.
to zero.
Hmm.
So does it ensure that A is invertible?
So yeah. You are right. So the solution to is is only, let me add only here, right? Is only x equals to zero. Now is this
Okay.
right?
Yeah, now it's fine.
Now it's fine, right?
Right.
Yeah. So basically you need
Okay.
to show this in both directions. If x equals to zero, then the matrix has to be invertible. If matrix is invertible, then only x equals to zero is possible. So yeah, you are right.
Right. Okay, sir.
Yeah, sorry.
Sir, actually,
Yeah,
you're telling something back then while saying that scalar triple product. You said ki
Yeah.
there's an interesting thing when it
Uh,
can be like you're going to say something, but you didn't
yeah.
finish. So
Yeah.
yeah.
So yeah, about the scalar triple mode, I was just saying that. So when you look at this kind of system, right? So we were looking into this. What happens when R3 dot R1 cross R2 is essentially zero? When it is zero, when the determinant is zero, right? When
Mm,
determinant is zero, when the matrix is not invertible. Matrix is not invertible, right?
right.
So basically,
Yeah.
this was was trying to say key. That's
Okay.
it.
Okay. Right. Right. Yeah.
So I think another student has some doubts. Shiv Kumar, what is the
uh,
doubt you have? You are raising your hand. Can you explain your doubts? Am I audible? So I think he don't have any doubt. So Satinder, you were trying to say something. Can you just quickly say
yeah,
your doubts?
yeah. I'm saying ki like if the matrix A is not invertible, like if it is singular,
Yeah,
then it may happen that the for out of infinite many solution X can be zero also.
yeah. Trivial always exists. Trivial solution always exists.
No, no, that I'm trivial. I'm not saying for infinite many solution. I'm telling
Huh.
ki like
There are
is
infinite many
uh,
solutions plus zero is also a solution.
is it there? Can we see any example? Ki other than
Uh,
zero, it will come.
So you are
I
so
think
you want an
zero
example
we are not
where
going
there
to
are
hit.
infinite many solutions? Huh?
Infinite will be there. I think maybe zero is we are not going to hit, because once we are at the zero, so we can't move forward now, I think.
Okay, you are saying if the matrix is zero, right?
No, x vector. Like if A is singular matrix,
Ah,
A
right.
is
Yeah.
singular matrix.
Hmm.
So is it confirmed कि we are going to get x equal to zero plus other solutions also?
Yeah, if you are trying to solve ax equals to zero, right? If you are trying to solve the homogeneous systems of equation,
Yes,
uh, so then in that case, you always have a solution that x equals to zero. That is all that always exists. This is the
always,
trivial
always.
solution that always exists, right? Because A can be any matrix and you are saying ax equals to zero, then x equals to zero is natural choice. It is there already, right?
Yes, yes.
And then plus other solutions, non-homogeneous solutions, non-trivial, sorry. Yeah. Plus non-trivial
So
solutions that can be either zero, one, or infinite. So this is
so
how the
that's
set looks
why
like.
in this option we have to add only. Otherwise, it
Yeah,
will
that's
be
why.
if only is not written, then it will be invalid.
I mean, yeah, it's not a complete statement, I guess. Then the solution to x equals to zero is x equals to zero if and only if matrix A is invertible, right? So this will not be a valid inference, right? So let's do one thing. Let's say that this is not a valid inference. Khatam, right? This is also not valid. So I can always choose option C as also our answer. Yeah, you're right. Thanks. So option D says the solution to the equation ax equals to zero is the set of vectors in if the three column vectors are in the same direction, right? Is the set of vectors in the plane. The solution to x equals to zero is a set of vectors in a plane if the three column vectors are in the same direction.
We have done
Ah,
that
that's
one.
true.
I
That's
think
true. This is a valid. Yeah. We already saw this example, right? Yeah. So what do you have doubt?
I
My
don't
doubt
have doubt.
was
I've said
that matrix A invertible means all the three vectors, or rather the component vectors, are linearly independent, right?
Invertible, right? Yeah. Huh. Linearly
Ah,
independent.
independent. Okay.
Right. So Shiv Kumar, what was? Sorry,
So there
Satinder,
is no
what you?
question of raising an issue of linearly dependent there, correct? In
Uh,
option B, when once you
Option
say
D.
matrix A is invertible,
Yeah. Hmm.
then the three vectors are linearly independent, correct?
Yeah, independent. Yeah.
Independent. So there's no question of raising doubt regarding dependence, linear dependence and all. No.
Okay. Yeah.
So in that
So
case, that only and all is not required, I think.
no, no. The thing is, what the students were trying to say is, so let's say the solution to ax equals to zero is x equals to zero, if and only if the matrix A is invertible. So it is saying if the matrix A is invertible, then only you get the solution x equals to zero. And the doubt was, let's say if the matrix is non-invertible, then also you get the solution x equals to zero, right? That's always true, right?
Okay.
So that's why this statement is not a valid inference. That's it.
Okay.
Yeah. So let's move on to option number. So yeah, Satyendra, what was the doubt you had? Satyendra, can you
no, I
explain?
don't have the doubt. No, I
Who?
don't have the doubt.
Okay, who had
I've
the
said
doubt
ki,
for?
we have discussed.
Uh, yeah. So who had the doubt for option D? No one. I think option D is clear. This is the point where I was saying that you will have infinite possible directions as well as magnitudes. So basically, if all the three vectors lie on the same line, you will have a space, a two-dimensional span, right? So that is what it's saying. So ax equals to zero, the solution is a set of plane vectors in a plane. This is a plane perpendicular to all the three vectors which are along a line, right? Which are normal to this plane. Yeah. Anyone do you have any doubt in this? Great. Let's move on to the next question. So let A equals to this, U equals to this. If A equals to L the L matrix is, right? So let me look into other questions which are more conceptual. I want to answer them, and then I will come back to these numerical problems, right? So you can do this problem, right, on your own. So let's say if A is this and U is this, and if A equals to LU, then what will be the matrix L? You know the formula for LU decomposition. You also know how to get to that formula. Both things you know. So I hope you will be able to figure this out. So let me do this towards the end of the session if there is time, or I will carry forward in the next session. But right now I want to cover the conceptual questions, right? Is this fine with everyone? You can figure out the solution for this on your own. I will eventually solve this, but till then you can do this, right? Great. So let's move on to the next question. So yeah, suppose EI for I equals to 1 to 5 are 1, 2, 3, 4, 5 are five elementary row operations that are applied on the matrix A such that E5, E4, E3, E2, E1 into A equals to U, right? Where this is what we saw in the LU decomposition notes itself, where U is an upper triangular matrix, then the lower triangular matrix L is. What will be the lower triangular matrix L, right? So there was a small detail that we ignored till now, that I ignored entirely. I was saying, so you do these row operations, right? You this row elementary row operations E5, E4, E3, E2, E1 into A is equals to U, right? Now these are elementary row operations and these are lower triangular, right? Fine. Now the question is, what will be the L matrix, right? So now let's say I'm saying that A equals to LU. So naturally, what it looks like is I am saying that L inverse A is equals to U, where L inverse is essentially E5, E4, E3, E2, E1, right? Naturally, this looks like, right? Now you can say from there, you can say that L equals to E5, E4, E3, E2, E1, and take the inverse of it, use the property of inverse or product of matrices, and you get to the answer, which is option C, I guess, right? Which will be the option C. But I'm saying this is not the correct answer given only this kind of information. Why? Let's look into this. Easiest way, let's say U is a zero vector. We are saying U is upper triangular. So this is also an upper triangular matrix, right? No, let me not take this. This is a very trivial case. But let me take some good example where it becomes 100, 010, 000, something like this. So let's say this is your U matrix, right? Fine. There are no non-zero elements below the diagonal. Fine. Everyone agree with this? Fine. Now you can see that U is singular. This means E5 multiplied up to E1 into A is singular, right? And if let's say you know that A is non-invertible or even invertible, right? Let's say A is non-invertible. Then in that case, E5 multiplied till E1 are not singular. This means you can't do the inverse, right? You can't find the inverse of this matrix. So this will not be happening at that case.
Sir,
Yeah,
so one doubt. So
yeah.
elementary matrices are always what should I say? Elementary matrices are always that non-singular, right?
Uh, it's let's think of this. Can we figure out something? Um, oh,
I
zero,
think we
zero,
don't
zero.
have to consider this.
You can think of like this. R3 equals to
Just
R2 plus 0 R3. Something like this.
like sir, excuse me, sir. So
Uh,
Yeah.
instead of
this
taking
is
all together,
possible.
we can take one by one. We can take one by one on inverse. Like we have E1 uh, on the A matrix. We have applied E5 first we have applied E1, E2, E3, E4, E5. Now one by one we'll take the inverse, because to the left side we have E5. So first of all we are going to take the inverse of E5. So we have got E5 inverse. Now we take the E4 inverse. So one by one will, instead of taking all together, so I think we'll can come to that in that form.
Yeah, right. That's right.
Satendra sir was saying something different, I think. So he was saying elementary matrices, are they always invertible or not? Like taking them one by one or taking all at once are basically the same thing. You're just doing it all at once. Either, yeah.
That I think singular and non-singular depends on A only. Because if A
no,
will be non-singular, then will not.
The question is that elementary matrices, are they always linearly are they always non-singular or singular?
You're right. The question is right, because I'm thinking of that. But we all know this property. If you apply elementary row operations, you don't change the determinant of the matrix, right?
Right.
So they
sir,
are
in your example, no?
they have to be
You multiplied 0
non-singular.
with R3. So I think that is not an elementary
So
operation.
this
While
is
you
not an
multiplied 0 into
elementary. Yeah, this is not an elementary row operation. So then in that case, this will be true. Option C will be true. Yeah,
Okay,
that's
sir.
true.
Yeah.
Yeah, thanks.
So, sir, but still, I'm trying to get your point. So you were raising the concern that this question is right only when like LU decomposition is possible. This kind of thing you are raising.
But LU decomposition is like it will stop when you try to do something on a singular matrix, right? Because you don't get a pivot element to do the subtraction further.
Right. Let me think.
No, but you will again get a lower triangular form. You will again get, right. It will stop, but you will get a lower triangular and upper triangular form. So yeah, Rohan,
So
what
can
was the
you
doubt?
just give me your statement? Can
Yeah.
you give me the statement which I can check later? That so you're saying that for non-singular, for singular matrices, what LU decomposition will look like, right? This kind of thing.
Yeah.
Okay.
It will exist. Yeah.
Okay. I haven't done this actually earlier, so I will check it once.
Okay. Yeah, so basically there is some property in that you will look on to later on, right? It essentially depends upon the matrix, if the matrix minor principal values are 0 or not. Yeah. So that is something that is not covered in the lecture. So we should not think of if the LU decomposition exists always or not. So basically in that case option B will be true, but the thing is you don't know about that right now. So
Excuse me, sir.
yeah.
Sir, like what I was thinking, uh, uh, whatever the operations we are applying this one to decompose into LU, but
Yeah.
our final answer will depend upon the input, what input vector we are going to do, because A we have decomposed into LU, and then X vector, what the X suppose we want to solve AX equal to B. Now A, what I have done, I have decomposed into LU. With that we will come to know that whether we get B or not, because
Yeah.
I think it will be related to that. So
Yeah.
No,
So here there is no B, na? Like
no,
only
yeah.
A is there. Okay. Yes, sir. Go on. Sorry.
Yeah, you are right. Basically, we are not interested in B right now, right? Whenever we do matrix factorization, we do some factorization that is independent of the vector B, and then use that
and
vector X.
I'm not saying that, but I'm saying ki when we are talking about for the singular or not, decomposition will be there or not. So when there will be the system of equation in that scenario, we have to think once. That I was saying. In this case, though, in this question, though, we don't have to see that part. But if that is a system of equations, I think in that case, what you are discussing, what you have explained, that part we have to think once. That I was thinking of.
Like,
What you're explaining a singular or that part. So when we have to solve the system of equation, then I think that problem may arise.
what problem?
Like I'm saying, sir, you are explaining that one. You will be singular or not. That cases we are discussing. So I was
Right,
saying
right. But
that
yeah.
problem will arise in the equation system of equation.
No, basically, when you are writing a matrix as A equals to LU, whether any one of these matrices is singular or not, it doesn't depend on this equation, right? These are completely unrelated right now. You are only dealing with the matrix A and trying to write it as a product of lower triangular and upper triangular. That's it. You don't want to do anything else from it.
Okay, sir, I think I got your point. So suppose A is a 3 by 3 matrix, and can you confirm you are trying to mean this? The third row
Yeah.
is a linear combination of first and second rows. So
Okay.
after performing elementary row operations, the third row
Hmm.
will vanish. So it will be zero
Yeah.
completely.
Yeah.
So we have two operations multiplied with A that will give us a U. Because the first example that you gave, no, that is a zero matrix is also a upper triangular matrix by
Yeah.
definition.
Yeah.
So yeah, I think you're right that it will always happen. Maybe one thing might be troublesome, that
Hmm.
pivot in the first row might not be there, but we can still
Yeah.
permute it and do with those things.
Yeah, that is the thing I wanted to get to. But yeah, I am not sure if you are taught about that. Because in the notes, I only saw the point that LU decomposition is something like this, and that's it.
Mhm.
You are not. So that's what I
Yeah,
was saying. Let's say if the matrix A is singular and you are trying to get the pivot to get to it to zero, you won't get that. So it will
right,
stop
right.
you.
Okay,
So
okay, now
that's
got you.
why, yeah. So can we
Okay,
safely
okay,
say
now
that
got you.
option B is true and it is explainable to everyone, understandable to everyone? So how to get to this answer is basically what I am saying is consider this kind of matrix 0, 1, 1, 1, 1, 1, and 2, 3, 0. Something kind of 2, 3, 1. Let's be more safe. Let's play more safer on the safer side. Or maybe this kind of matrix 0, 1, 1, 0. Right? This is a full rank matrix. This is invertible, right? Still, the LU decomposition doesn't exist. Anyone, can you, from the algorithm that you have already seen, can you figure out the LU decomposition for this? Can you perform Gaussian
So,
elimination on this?
but sir, with the given information, they say that upper triangular matrix exists. So if you take that into account, that they're saying no, that U is a upper triangular matrix. That is,
Hmm.
they are completely ruling out this option. That so
Okay.
what they are giving is LU decomposition is possible. Otherwise, you wouldn't be there.
Okay. So, right. So let me think of this. So I can write this as. Mm, hmm. Okay, so yeah, you are right. If basically LU doesn't exist for this, I'm trying to figure out, can we write this matrix as a upper triangular matrix as and some lower triangular matrix as a product of these two. So let me write this X Y Z 0 and A B C 0. Acha, so then it will be overdetermined and I mean underdetermined. You can't solve the equations. Hmm. So I was trying to think of this example. Yeah. So let's say for the best case scenarios, option C is true. So this answer is not completely explainable to you guys right now because you don't know everything about LU decomposition. But you can always get this option C to be true if the matrix is invertible and you are getting the pivot elements every time whenever you are trying to do the decomposition. But if you are not getting the pivot elements, you will need some sort of row permutation, some sort of matrix permutation, matrix product that will essentially give you the final decomposition. But that is not LU decomposition purely. So that's something we'll have.
Sir, one thing to just ask,
Hmm.
one follow-up question from this 2 by 2 matrix that you wrote. So can we
Yeah.
safely say that for a 2 by
Hmm.
2 matrix, LU
Hmm.
decomposition is always possible? Can we say that? Because swapping two rows is also an elementary operation, right?
Basically, swapping two rows is a change of rows is a permutation operation.
Yeah,
So let's say you are saying elementary is saying R2 is equals to R1, right? R2 is replaced with R1.
right, right. For 2 by 2
This
matrices only, okay.
I'm
So
not
that
sure
I
if
don't have.
this is not the correct definition of elementary row operation as far as I remember.
Okay, so the three elementary row operations we have, one is scalar multiple, a non-zero
Yeah,
scalar multiple of any row.
yeah,
Second
yeah.
one is multiply a
Non-zero
row.
scalar
Third
multiple,
row
right?
option is,
You remember
yeah,
that property, right? Non-zero scalar multiple, right?
right.
So you are saying R2 equals to 0 into R2 plus R1, right? Is this is not possible, right?
But isn't swapping also a valid elementary row operation? Can you
I,
tell me the three
I'm just
elementary row
saying,
operations?
I'm just, okay, yeah. Let me open up this.
Yeah.
Ternary row operation. So basically the criteria for operation to be defined as elementary row is that the determinant should not change. Okay, row switching is possible, right?
Right. So actually, I
Mm-hmm.
got your point. That's why I added that 2 by 2 matrix thing, because for a complete permutation matrix, many rows might be permuted. But
Mm-hmm.
when we are saying that it is 2 by 2, only a
Mm-hmm.
switching of only one row is possible. So that is an elementary operation.
Yeah.
So even if you are creating this kind of instance 0 1 1 0, I can always
Mm.
multiply it by a permutation matrix, which is
Permutation
actually
matrix,
elementary
which is,
matrix,
yeah.
and
But
that will in turn always give us LU.
but the thing is, will it be lower triangular? So you get this, right? 0 into this 1 0 0 1, right? So this is the permutation matrix, but right now the matrix is not this is not the original matrix, right? You have transformed the matrix to some other matrix. So the input matrix was
Okay,
0 1 1 0, right?
okay, right.
And now you are transforming this to a matrix 1 0 0 1, right? Using
Mhm.
some matrix product which is not a lower triangular operation, which is not a lower triangular matrix, right?
Okay,
So this is not
right.
a trans. So basically, you get. Let me write it like this: L
Uh,
inverse P A
uh,
equals to U. So you get P A equals to L U.
actually,
This is not the vanilla
Right.
LU
uh,
decomposition.
uh,
Fine.
Okay.
sir, I am I getting the wrong point here? Like
What?
maybe I'm misunderstood. I think
Hmm.
whenever we are applying the elementary row like transformation on A matrix to
Yeah.
decompose for LU part, so
Yeah.
elementary is not always lower. It is not necessary that the what the elementary we are applying it should not be lower because its inverse will be
Hmm.
lower. I think.
Yeah, right. Swapping matrix is not a. If you figure out the matrix for this swap operation, it's not a lower triangular matrix. You are right. Yeah. So basically, LU does not
So
exist for that case. So if you want to get the LU decomposition, you need to think of
no,
something like, yeah,
I'm saying ki elementary whenever we have to apply for the LU decomposition, so
hmm.
elementary will be always lower only. This is
Yeah, yeah, because we are trying to find out a product of lower and upper triangular matrices. That's why
uh,
we need that.
okay.
So
So what
basically, if
elementary
you
we have applied here, it is not
so it,
the lower one. That's why it is not possible.
yeah, that you can't get a LU decomposition out of this matrix directly. You can never get this. I mean, that's why I was trying initially. What I was trying to say is, can we figure out a product for this matrix? But even unfortunately, I was not able to get some example for this because you will not get an example. Is this clear, Rohan?
Right. Yes, sir. Yeah, it's clear now.
So basically, it's something you have to pay attention to the details, like what operations are actually you are doing. Here, P is not a lower triangular matrix, so essentially, it will not be a complete lower LU decomposition.
Right. Yeah, got you. Yes, sir. Now clear.
Fine. So I think then yeah, then L is not a lower triangular, so it's options B is anyways correct. Because this inverse might exist. Basically, option C might be true, but any of one of these matrices E might not be a lower triangular matrix, making this a non-triangle matrix, right? So basically, option B indeterminate with the given information. How we reached to this
Sir,
answer? We started with some. Yeah.
yeah, I got that permutation part, but still,
Hmm.
isn't it the case that C is always true? Because only the thing that U exists, they are given that
Yeah.
whatever elementary.
Yes. C
Yeah.
C is true. You are right, and U exists. This is also right because you we saw this example, right? L inverse
Okay, okay, I
into
got you.
P into A is equals to
Right,
U,
right,
where
right.
U is a upper triangular, right? So
So your argument
U
is P is
exists.
also an elementary matrix. P is also product of elementary matrices,
Yeah,
but
yeah, yeah.
okay, okay.
So
So I
P is
think
also a
this
product.
elementary, yeah.
Hmm.
Sorry, sorry, go
Yeah.
on.
So what I'm saying is, just to clarify on this answer, option C is always true, but there is one more condition that the question is asking, that a lower triangular matrix L is, right? So this condition has to be satisfied, that the matrix L has to be lower triangular. Now, in this case, L will not always be a lower triangular matrix. What I'm trying to say here. That's it. That's why indeterminate with the given information. Now go ahead. Go ahead.
Okay, sir. Now got you. I think the reason we are having this confusion is because they haven't mentioned what kind of elementary row operations you are performing. So that
Very
gives
good.
us a loophole. Someone can
Hmm.
think a permutation might be there, and that's why
Ah,
the like lower triangular won't come while taking
yeah,
inverses. Okay.
Excuse me, sir.
yeah,
Like what I have the doubt, like uh, E5, E4, E3, E2, E1
hmm,
operations
hmm,
we are applying on A,
yeah,
and that is equal to upper triangular matrix.
yeah.
So whenever we are going to take the inverse,
Hmm,
so whatever its value will be, like
hmm,
let it be any C matrix. Like inverse of all will be C matrix. So
yeah.
C matrix multiplied by the upper matrix
Okay.
definitely is going to change A.
Yeah,
But the A will be not same. Like because whenever we
yeah,
are taking the inverse, so when we
yeah.
are going to
That's.
multiply, if it is not lower triangular, so when we are
Hmm.
going to multiply with the upper triangular matrix, so definitely the A part will be not same. We are not
No,
going to get A.
no, you will
So
get A. You will get A.
no,
You
no,
will get
no,
A.
no. If it is, I think we can't get.
So what you are saying is, let's say the product of these matrices E5 into E4 up to E1 is some matrix C, right? Yeah, let's say C
Yes.
inverse, right? And then you are saying that if we write the term C into U, you are saying C into U will not be equals to A. That's what you are saying, right? Satinder, are you saying this? I think you are muted.
Uh, I'm saying if U is the upper triangular matrix, if it is
Yeah,
satisfying that part,
yeah.
so uh, then
Mm.
definitely C should be either it will be a lower triangular matrix, then only it will be equal to A. Otherwise, that case will be this equation is invalid only. What
So
the
you are saying
operations
that
we are
CU will not be equals to A, right?
uh, uh, like what I'm saying, I'm just saying the mathematical equation.
Okay.
What the operations we have applied, we have
Hmm.
applied on even operation. We have applied even operation on A.
Hmm.
We are applying only on
Okay,
A to
right.
get
You are
upper.
saying any of one of these operations, if the matrix is not lower triangular, you won't get a U. That's you are saying, right?
I'm saying we are getting U because
Hmm.
of we are applying even. That's why only we have got U.
So you
We,
are saying
we,
E1 has to be lower triangular, right? All of these E's has to be.
this only I'm saying because
Mm,
equations to
No, no,
place
no,
we have got this.
no.
So that's why
But that's
C.
not true. Yeah.
No, no. I'm saying I'm saying sir, कि the equation is saying कि from A matrix
Hmm.
even operation we are applying to get the upper
Hmm.
triangular matrix. So
Hmm.
we are getting the upper triangular matrix. It means that the upper part of the elements are matching with the A elements.
No, they don't match, right? There's a
No,
matrix product going on,
no,
right?
I'm not saying like the question says in the question it is written. If you see the question, it is written कि A matrix is such that applying these operations and we are
Huh?
getting U.
Okay.
So applying these operations, if we are getting U, it means कि what the upper elements of the upper row elements are there of U,
Hmm.
definitely they are of A. Hmm.
No, no,
May,
no.
may,
Uh,
I'm
let uh, let's finish this. Let me take an example, Satyen. You guide me, okay?
yeah,
Whatever you
yeah.
are trying to say, let's discuss this. Let's finish this quickly, right? So let's say I have the matrix A as 1, 1, 1, 2, 3, 5. 1, 2, 3, something like this. Now, what you are saying, just tell me quickly.
Okay. Equal to, let's write the upper triangular matrix on the other
Ah,
side.
right.
Upper triangular matrix will be row wise, I'm telling. 1,
Yeah.
1, 0,
1, 1, 0,
then 0, 3, 5,
0, 3, 5. Okay.
and then I think 0, 0, 0,
How are
or
you
1,
getting this upper
0,
triangular
0,
form?
1, 0, 0, 1. I'm just taking example 0, 0, 1. I'm taking any example.
Okay.
Is it upper triangular?
Yeah, this is upper triangular, right?
No,
Yeah.
sir, that you have written 0. Top row will be 1, 1, 1.
Okay.
Top one. U
Yeah.
matrix.
Yeah.
Is it upper triangular matrix?
Yeah, this is upper triangular matrix, right?
So actually, how we are getting this part? We are getting this part. So when we see on the left side A matrix, so on A matrix, let's apply the elementary transformation E1, elementary row E1. We have
Mm-hmm.
applied E1,
Mm-hmm.
E2,
So, but
E3 to get this part. So this part we have
basically,
got from A only. It means
so
ki if you are getting after applying the elementary row transformations number of times.
let me stop you there itself. This
Okay.
is a random matrix that you are building up, right? So you can't think of the properties of a matrix or of a matrix product if you take a random matrix. This is some matrix that you believe is the upper triangular matrix. But I'm saying that
Huh.
there are infinite upper triangular matrices of such kind that will give you L plus U equals to A, right? So it's simple question. A plus B equals to 3. What are the values of A and B? Infinite possible values, right? So this is something that you are thinking out of random. Like this is some matrix. So for sure, all others have to be a lower triangular. That's not true, right? You have to prove this
So,
claim if you are saying this.
uh, and you're right on that part. Like at random, it can't come. I'm not saying what you have explained. I've understood. You're right at
Yeah.
your point. But I'm saying the question says this. In the
No,
question,
no,
I
no,
think
no, no.
it is saying this part.
No, 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 no. I think you are reading it wrong. So basically, the question is only saying that you do this matrix products and you get some upper triangular matrix. It's not saying it contains the upper part of the matrix A. That's it. Don't think
Maybe
of
some
anything
other
else.
it may be some other upper part
Yeah,
matrix.
it's some upper triangular matrix, not necessarily containing the elements of the matrix A. Yeah,
Got it. Got it. Got it.
fine. Option A, four clear. Right. Anyone else? Do you have any doubts?
No, sir. Sir,
Great.
Shiv Kumar sir has something to say, I guess. So
Sir,
he is
yeah, what do you
unmuted
want to
for
say?
a long time.
No, no, the question you raised to us that sorry, on the right hand side, U is upper triangular.
Hmm.
Okay. But the question is on the lower triangular matrix L,
Hmm.
which is on the left hand side of A.
Okay.
That is the question. He is
Yeah.
relating that to the upper triangle on the right hand side, which is wrong.
Okay. Yeah.
Because
Fine.
that E5, E4, E3, E2, E1
Hmm.
operation, after
Hmm.
doing,
Hmm.
you will end up with a lower triangular matrix on the left hand side.
Yeah,
On the
but
right
when you
hand
take the
side,
inverse of, but you take the inverse of this,
that on the right
if
hand
it,
side it will reflect as on the right hand side it will reflect as upper triangular matrix. But the
so you're
question
saying,
is the lower
yeah.
triangular matrix L is like L is E1, E2, E3, E4, E5, which is
Uh,
not correct.
uh,
Indeterminate with the given information may be right, may not be right. C, L equals E1 inverse, E2 inverse, E3 inverse. That part I don't know how to define. Then the D, E5 inverse. That means each row operation you are taking inverse. Isn't that? E1 is one event, say
hmm.
one row operation. E2
Hmm.
is another event that
Yeah,
you are
right.
taking.
Yeah, yeah.
So whether each inverse has to exist or should may not exist, I'm not sure.
Hmm.
So the safest answer would be the B,
No,
indeterminate with the
let me
given.
get to this. This is not the safest answer, or there is nothing wrong in this answer. This is the correct answer and this is the only answer. Why? Because the
Uh,
question says, does there some lower triangular matrix L exists such that if L into A equals to U for each matrix A? The question is this true for all matrices A? The answer is it is not no, first of all. And the option B says indeterminate with the given option. That is true. Why? Because you can always get matrices A such that, for example, this matrix that I picked up 0 1 1 0. For this matrix, you won't get a LU decomposition directly. You won't get a LU decomposition. For this, you have to do some pivoting where even so Rohan is right, even can be a pivoting operation P, permutation operation P. So then if it's not, if it's a permutation operation, it's not a lower triangular. And if you are multiplying some lower triangular part matrix with some normal matrix, you get a normal matrix. That is not necessarily a lower triangular matrix. So basically that's why L option, given that option C is looks correct, but the only thing that lacks in option C is L may not be lower triangular. That's it. That's why option C is not correct and option B is correct. Why? Because this is not defined for the given information. It will be clear if it's given that we are doing permutation or not. That's it. So option B is not the safest. It is the answer.
Thank you, sir. Thank you.
Yeah. So, Rohan, do you have any doubt? You are
Uh,
typing something.
uh, excuse me,
No, sir.
sir.
Yeah. This one.
Yeah.
It means the I think the condition will be same. B option is correct. I agree.
Yeah.
That is in spite of applying the elementary rows,
Hmm.
although it is not mentioned that elementary rows will be lower triangular only, or maybe what
Hmm.
it may happen that it inverse doesn't exist after applying
Um.
that.
No. For elementary row operation, inverse exists. Inverse exists
Okay, okay.
because you are doing either row transformations or some non-zero scalar product plus addition. So basically, nothing goes into zero. So if you look into elementary, all the row, just write down all the elementary row operations, try to write them as a matrix product. You will see that none of the elementary row operations is a singular matrix. That's what I'm saying. Because why I am saying this, because I myself don't remember all the elementary operations, but I remember one property. The property says that doing an elementary row operation does not change the determinant of the matrix, does not change the rank of the matrix. So if it does not change the rank of the matrix, then it can't be a singular matrix. That is one property. So basically, when you figure out how, so in linear algebra, essentially, whenever you are defining some quantity, right? Let's say determinant, so you define some properties associated with it. Then any function that satisfies those properties is essentially that function. So for example, determinant has the property that it's the volume occupied by the parallel pipe or the area of the span area of the vector parallelogram. So this is a property, right? That's why you get this. Even the cross product, you must have seen in the lectures also that uh, everyone says that cross product gives you the area of the parallelogram found by the two vectors. But why? Because when you work out the equations, you will see that this is essentially the area of the parallelogram. It's not something that is a magic. It's just that it's there. So that's why, yeah, that's why in linear algebra, everything is, as you can prove everything from scratch. So yeah, fine. Anyone else? Anyone else? Any other doubts?
No, sir. We can proceed.
Great. Thanks. So I think the time's up, but still I want to get to some conceptual, finish up some conceptual problems. So basically, the problem with this week that I found myself is the week was very fast by from in the lectures also, because all of a sudden you were taught about LU decomposition without and also the homogeneous equations were covered. So I think it was quite lengthy. I will finish up in the second lecture session in the next session very quickly. But let's solve this fifth problem and then end there, right? This is the last problem for today's session. Just finish this and end here. It's a very simple problem. So let's say A is a 3 by 3 matrix. Which of the statements is true? It can never have zero eigenvalues. Let me finish up the equation statement. It can never have zero eigenvalues. It has all three eigenvalues and whatever. Like, so first thing, how to find the eigenvalues of a 3 by 3 matrix. So what is the definition of eigenvalues? We know this, right? Eigenvectors, comma, eigenvalues, right? So we say a vector V is eigenvector of matrix A if and only if AB equals to lambda V for some scalar lambda, right? Scalar lambda belongs to, it can be a complex number also, but let's consider the real values and real matrices, right? Now, how to find the eigenvalues? It has covered in the lecture. So it says AV minus lambda V equals to 0. I can always write this as, that implies AV minus lambda into identity matrix I of the same dimensionality as A. So I is the identity matrix, ID matrix belongs to R3 cross 3, right? So now from here I can write it A minus lambda I into V equals to 0. And let's look at the matrix M, which is A minus lambda I, right? So you are saying MV equals to 0. What are the solution to these systems of equations, right? So it all depends on the matrix M, right? One trivial solution is V equals to 0. Trivial solution is always there, right? The question is, A is a 3 by 3 real matrix. Which of the statements is true? Option A, wrong. 0 can be an eigenvalue if the matrix is singular
Sir,
matrix, right?
sorry for interruption.
Yeah.
Last time you said V's can be 0, right? One trivial option is V0 or something like that.
Yeah,
Can you scroll down?
yeah.
But V can never be 0, right? V is an eigenvector. So eigenvector can never be 0.
Oh, sorry.
The thing can be, M can be 0, right?
Yeah. Eigenvector can't be 0. Yeah. I mean, eigenvector can be 0. In fact,
No,
let me think.
eigenvector by definition is not 0.
Eigenvector is non-zero. There's a definition. V can't be 0, right? Yeah. Trivial can't exist.
Right.
Yeah, this is the definition of eigenvector. You're right. So I was thinking in terms of eigenvalues. So lambda can be 0. That's what I was thinking. Yeah. Lambda can be 0. Sorry. Yeah. Eigenvector can't be 0, but lambda can be 0. So eigenvalues, it can never have 0 eigenvalues. That's false. Lambda can be 0. Why? We know this. V is non-zero and lambda can be 0. It depends on lambda. Why? We will see this. Now, other three equations ask us to figure out the properties of this matrix M, right? So how does matrix M looks like? It is the matrix M A minus lambda I. Now you want to figure out that A minus lambda I into V equals to 0. That means you want to ensure that the determinant of, so basically if V is not 0, if you are not considering the trivial solution and you are saying other solutions exist, why they exist, determinant of M has to be 0, right? Am I right here? Is this true? Since V can't be 0. Am I right in this? If V can't be 0, determinant of M has to be 0. That means determinant of A minus lambda I has to be 0. Am I right here? Everyone?
Yes, sir. Yeah. Right.
Fine. Now then what you have to do? This is the information you have. Just figure out the solution, right? So let's write up let's take some random A matrix. So A1, A2, A3, A4, A5, A6, A7, A8, A9, minus lambda I, right? 1, 0, 0, 0, 1, 0, 0, 0, 1. And find the determinant of this matrix, right? Clear the page. So
sir, one
it
thing.
becomes, yeah. 2, 8, 3.
So for
Go on.
For claiming option A to be false, isn't it only enough if you come up with only one counter example and you can show that 0 is an eigenvalue? So
So you can show this example, right? 1, 0, 0, 0, 1, 0, 0, 0, 0. So let's take this matrix and you can write it as matrix 1, 0, 0, 0, 1, 0, 0, 0, 1 into 1, 0, 0, 0, 1, 0, 0, 0, 0 into this inverse. So basically it's again identity. So again, this is the eigenvalue matrix where eigenvalues are 1, 1, 0. So 0 can be an eigenvalue. Yeah, that's right. So A9 minus lambda. Now you figure out the determinant of this matrix. But one thing I can say for sure from this matrix for the determinant equation, it will be something like A1 minus lambda into A5 minus lambda into A9 minus lambda. You will get something like this. This will be exist in the determinant. When you take the determinant of this matrix, you will get this plus something else, something like, let's say something, some XYZ, right? And this will give you a polynomial of degree 3 in lambda. So you will get something like C1 lambda cube plus dot 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 plus C Z1 2 so C2 lambda square plus C3 lambda plus C4 equals to 0. So this is a cubic equation. You want to find the number of roots. You want to find the root of these equations. So it can have either 0 as a solution always. There's a possibility, not always, but there is a possibility. It can have one real, two imaginary, which are basically complex conjugates. It can have three real roots, right? And in this case also, they can be distinct or equal. So these are the three cases that you will see for the root finding problem for this cubic polynomial, right? So I think this is clear to you, everyone. So from there we can answer this problem. It can never have zero eigenvalues. Wrong. It has all three eigenvalues to be real. That's not true even for a real matrix, right? This is also wrong. Even if the matrix contain all the real entries, it's not guaranteed that all the eigenvalues will be real. Third option C, it can have at least two real eigenvalues. That's not true because it can have one eigenvalue and one real and two imaginary eigenvalues. So it says at least. At least means there are at least two real and then something else. But no, there is, if there are imaginary roots, they have to be in pairs, complex conjugate pairs. So basically, at least one real eigenvalue will exist. Option C is also not true, right? So basically, there is not, you can't have sorry, two real plus one imaginary. This is not possible. You can't have this.
Uh, Option A, it can be it can never have zero real eigenvalues, I think, because eigenvalue can be zero also.
Yeah, we can add another option key. It can have zero eigenvalue, something like that, right?
Zero, no, just
Zero
A
real.
option
Huh.
zero real.
Zero real.
So at the
That's not
top we have to
true.
write.
This is also wrong, right?
Hmm. So, so option A will be to what is written. I think it will be true.
It can never have zero eigenvalues. That's
Acha,
wrong, right?
never. Acha, okay, I'm not focused on the
Sir,
never.
E has to be, by logical reasoning, E is always right? Because you're saying it can have. So it's not like it always have. So it can have zero real eigenvalues is always true because there are possibilities. I can give you one example which you already gave now, 110 in the diagonal.
Okay.
And I can say, sir, I have given you a matrix which has zero real eigenvalue. So
No,
it is all about the logical reasoning.
No. What I'm saying is not the zero as the eigenvalue. I'm saying no zero, no real eigenvalues. It is saying all the eigenvalues are imaginary. It is essentially saying all eigen.
Okay. Sorry. Got you. Yes, sir.
Uh, yeah. So basically, the only thing you have to take care of is how this characteristic polynomial. So basically, this polynomial that we got is the characteristic polynomial. This is also known as the characteristic polynomial for this matrix. And you just have to look into this polynomial and the degree of this polynomial. And from there, you can figure out everything about the properties of eigenvalues, how they will look like. Fine, everyone?
Sir, I think I have doubt in C and D. So I was reasoning them to be true actually. So C says that it can have at least the part is at least. I'm concerned about that part. I want to break it down into simpler terms. So it is saying it can have it can have at Satyander, just let me finish. Just 1 second. Okay, go on.
Excuse me.
Yeah.
It can't be at least two, no? at least two to can't be there, because at least two means if two is real, so one cannot be imaginary. I think so, because that
Yeah, yeah,
case will
but
never come.
let's
Because
get to the Rohan's
imaginary
question,
roots.
what he's trying to ask,
Uh,
Satinder.
no,
Let's
he's. I
let
think
him
okay,
ask.
okay.
Yeah. Yeah.
So C says that it can have at least two real eigenvalues.
Hmm.
So what are the possible cases? At least two, like exactly two or more than
Hmm.
two, right?
Right. Yeah.
So let's say n is that number. Let's say n
Hmm.
equal to 2 and n equal to 3. So the logical thing, if we break it, so
Hmm.
for C to be correct, if any
Hmm.
one of them is right, then
Hmm.
can we say C is right? I'm
Okay,
not
so
concerned about actually the eigenvalue part. I'm concerned about the logical reasoning part.
okay, it can have. You are interested in the can have part, right? So it
Right, exactly.
says
And at least.
two or three. Any one of this is, if this is true, then it's true, right? That's what it's saying,
Right, right.
right?
Kind of. Yeah.
Yeah, in that sense, it's true, but the question is not intended for that,
Uh,
and let's not
so,
get
so,
into
so
this.
excuse me, sir. Uh,
Yeah. First,
two.
one second,
Just
Satinder.
like
Rohan, is this clear?
Yes, it's clear. But if suppose it comes in a question, like in an exam, so isn't it
Oh,
right to uh, correctly say that C is false? Sorry, C is
yeah,
true, because
yeah, yeah,
one
yeah,
thing will
yeah.
be satisfied. No? Three real eigenvalues it can have, so making the
Ah.
whole conjugate logical kind of thing to be correct.
So what you can do is you can mark it as the correct option, and then when they give you zero for this question, then you can raise a regret
Okay, right.
request, explaining your point,
Okay,
like why I'm right.
But
Yeah.
right, right.
normally imaginary quantities will come in pairs, no?
Yeah, yeah, yeah,
Yes, sir.
Normally
Yeah.
imaginary comes in pairs.
yeah.
So naturally the real value can be only single at that time.
That's true. What he's saying
Or
is
three maybe.
uh, two or three, right? So basically, he's saying three real values can exist. So three real eigenvalues can exist, and this essentially, so this is a set. Let's form up a set. Then you have a set of two eigenvalues or three eigenvalues, right? So basically, this is a null set of two eigenvalues, and three eigenvalues is a sum set, and then there is one eigenvalue and something like that. But the question is, do we have some, is the solution space, does the solution space look like this? That's true. So that's what Rohan is saying, but let's not get into that. I don't want everyone to pay attention to this thing, because it is something dependent on the question problem setter. So yeah.
Oh,
So,
acha,
so
okay.
yeah, Satinder, what you want trying to ask?
just I was not asking. I'm telling that when we are considering
Yeah.
at least two. So in that case only, ki at least two real to scenario will never come. At least two means ki I know the cases will be two or three.
Yeah.
So when we are considering, because you are thinking of two real, means ki you are going in the wrong direction. It can be because this case you don't have to think only. This I'm
Yeah,
saying. That's why the option will be B will be wrong. Mathematically, it will be wrong.
option C, right?
Yes.
No, no, it will be right. Basically, if you look how
No,
the
no.
way he's,
Sir, on
there
the
is a
computer,
or operation here, right? So it's
no.
or here. Huh.
uh, I'm saying mathematically point of view, it will be wrong because what is happening? First of all, you are solving the system of equation. You are not going in the logical aptitude in the beginning, because
I,
for the lambda value, you are going for the however you have to solve for the system of equation, and for system of equation, you can't say ki it will be at least two, because first of all you have to think of maths. Then we will go for that.
that's right, but you can always say that the answer is two or three. Like let's
No,
say I'm saying 2 plus 4 equals to 5, 6, right? So, so I can say answer is 6 or 7.
no,
And
we
if
can't say.
there is some option like the answer is 6 or 7, then you will choose 6 or 7, because
No,
in an or operation, if any one of this is a true, the entire equation becomes true. So
I,
it's something
I'm
that,
getting
let's ignore this. Let's not focus on this
oh,
thing, right?
I'm getting your point, but or case will in maths or case will use in that case only when that is possible, because in if you'll go in the circuit direction in the uh, two case that current will not flow, or maybe in that direction it is not possible to go. So at least two, if it is an exam, then it will be wrong only, I think.
That's fine. That's up to you, right? Like Rohan was saying that if I choose option C, will I get marks? I'm saying that you can choose option C, but for me it seems fine. You are sane in choosing option C to be correct. You just will have to explain the problem setter or who
Uh,
the grader that my
no,
answer is right. That's what
actually,
I'm saying.
I was not seeing in the case of the assigned value. I was seeing when you are going to expand the cubic equation. So,
Hmm.
cubic equation, we think of whenever we solve the cubic equation, we
Hmm.
have to see the nature of the roots. So, the nature of the roots says that what are the possible cases. So, we say one real, two real. We never say.
Satinder,
Yeah,
I think
yeah.
we got your point. Actually, so if you hear closely, so what sir is saying that what mathematically how you're calculating it, it is correct, okay? But how the options are given, na? So in the option, if it's little bit about logical thing. So the math part that you're saying how to calculate the values, you're right. But we can take some time to understand this. Uh, and
So let
yeah.
me do one thing. Yeah, Rohan, just let's do one thing. Let me correct this question. It has at least.
No, I think then we have to erase the at least part, right? It
It
can
has
have two real
okay.
eigenvalues.
It have. Let me let me correct this again.
Right, right.
Let
It
me
can have at
release.
least.
It
Okay, okay.
has.
No, it's
It has two real eigenvalues. Now the question is there is no ambiguity in the question and everything is clear, right? Now option
right,
C is
right.
wrong. Everyone
Yeah, then
fine. So
similarly
now
for option D also, we have to erase that at least. Otherwise, those things will come again.
it has. Sorry. It has it. At least. Yep. It has one real eigenvalue. Yeah. So whenever you are giving the exam, just ask the invigilators like the question is ambiguous. Just tell them.
Yes, it's fine. Yeah.
Yeah. Fine, everyone. Is this clear? Anyone do you have any doubts in this?
But in the exam, you can't change the question, no.
I mean,
What's the
exam is I don't know how NPTEL takes it, though I don't know, but exam is not always about getting the right answers. Exam is always about thinking if you are able to build up from the concepts, not in the
understanding? Yeah,
lectures. Yeah.
understanding.
So I don't think of I'm not least interested in the exams. I'm most interested in explaining you the things that yeah, this is how math works and can you figure out it on your own. That's it. So what happens in
Thank,
exam, I can't tell what happens in the exam, right?
thanks a lot.
Yeah. So fine, everyone. So I think there are no doubts for today's session. Most of the logical questions, conceptual questions are covered, right? So I will have some basic numerical problems I will solve in the next session. So let's meet then. So thank you all. So this session we will have the session again in the next week's from 6 to 8 on Friday.
Okay. Thank you, sir. Thank you, Satinder and
Thanks.
Shivkumar. The
Okay.
conversation was very
Thanks.
nice.